AMC 2020, problem 22. So,
Yeah. This one's probably the hardest one on the test. A positive integer n is fed into a machine, and it gives us an output, and it's kind of this wacky function. So it depends, it does different operations to n, depending on if it's odd or if it's even. So if n is even, we divide it by 2. But if it's odd, we multiply it by 3 and then add 1. So it's kind of unpredictable. That's probably what they were going for in this problem. And we start with this number 7, right? For example, if we start with 7, we multiply it by 3, add 1, we'd get 22, right? Because 7 is odd. But let's say we had a number 6, then it would be even. So we'd have to do 6 divided by 2, and we get 3. So anyways, it goes back to saying n equals 7. It goes to 22, right? But it's then it says that we take this output 22 and we put it back into the function. So 22, we put it into the function. 22 is even. So we divide it by 2 and get 11 as our next. But then it says put it into it again. Put it another 6 times. So 11, we put it in. 11 is odd. 11 times 3, 33, plus 1, 34. Then that's even. We divide it by 2, 17. It's odd. 17 times 3 plus 1, 52. It's even. We divide it by 2, 26. And we end up with 26 after we put it in 6 times. So it's kind of unpredictable. You can't really predict where the 7 goes to. We can't really like know that it goes to 26. And now it's basically telling us that there are different numbers n such that when you put it in 6 times, we get a result of 1. So 7, we put it in 6 times, it gives us 26. So we know that 7 isn't an answer for n, but there's other values of n it's saying. And we have to find the sum of all such integers n. So when I see this problem, I see a really weird function that is unpredictable. We're putting it in through multiple times. What I think of doing is working backwards, because we know our end result. We don't know our starting result, but we can hopefully work backwards from our end result. So this is our end result. We're hopefully trying to get back to 1. And what I think is that let's try to relate an input like I to an output O, right? Well, if I is even, then we know that I over 2 is equal to O, right? But if I is odd, then we know that 3 times I plus 1 is equal to O, right? And since we're working backwards, we don't want to have O in terms of I. We want to have I in terms of O. So if we move around the terms, we get that 2O is equal to I when I is even. And when I is odd, we get that O minus 1 over 3 is equal to I.
Andrew, I like the idea. You create backward function.
Yes, an inverse function.
That's great. Okay, let's keep going.
So we have 1, right? So for example, let's try to relate this number A back to 1, right? Well, we have a function for A in terms of the number 1, right? So either A, it has to be even, and 2 times 1 is going to be A, or A is supposed to be odd, which means that 1 minus 1 over 3 is equal to A. So in this case, we get A is 2, and in this case, we get A is 0. So we know that it's 2. We can go to 2, but it can also go to 0. Wait a minute. It can't be 0, because we just said A has to be odd, and 0 is not odd, which means that when we do 0, we're not going to multiply it by 3 and add 1 and get 1. We're going to say it's even, and then we're going to divide it by 2 and get 0 again. So we have to watch out for that, because whenever we multiply 1 by 2, we're always going to get an even number. So we don't need to worry about A being odd when we multiply by 2. But we do have to worry about A being even when we subtract 1 and divide by 3. So we need to keep that in mind. So 0 is not valid for this. So actually, the only number that can go in this space here is the number 2. So now we go on. We can plug back into these two equations. And if we plug in 2 into the first one, we get that I would be 4. And if we plug it into the second one, we get that I would be 1. No, it wouldn't be 1. It would be 1/3. My bad. Sorry. 1/3. And we know that it can't be not an integer. It has to be an integer. So 1/3 doesn't work. So it has to go to 4. Okay. So now we can do it again. So we go back into the function. We do 4 all over again. Let's plug in 4 as O. 2 times 4, that's 8. 4 minus 1/3, that's 1. So this is the first time that we have two different numbers that work, right? One is odd, so we know it works with this 3n plus 1. So we know that it goes to both 8 and 1. So now we're starting to see sort of branches in this working backwards tree, right? So what I'm going to say is we already know a lot of the results for 1, right? If we go 1, 2, 4, 1, the only next thing that 1 can go to is 2. Once again, because I just said 1 has to go to 2. And then 2 has to go to 4. And finally, we go 4 splits up into 8 and 1 again. So we see that we have this twice cycle. So it goes 1, 2, 4, 1, 2, 4. And then we can go to 8 or 1. So now
these are the steps,
yeah,
right?
Yeah, these are the steps. We're working backwards from 6 to 1. So now we have to work on 8. So if we plug in 8 into this one, we get 16. If we plug it into this one, we get 7/3, which doesn't work. So we're stuck with 16. And then we plug in 16. 16, we get 32 when we multiply it by 2. And 16 is the second time it splits because